Hello students, this is part 13 of the series of modules on linear algebra. In part 12 we started the topic on the solution of linear equations. Remember that we were discussing a system of equations represented in matrix notation of the form Ax is equal to B, where A is in general an m by n matrix and B is a n by 1 vector. B is an m by 1 vector. Okay, so A is an m by n matrix and X is the unknown vector, column vector containing the unknown coefficients, which is n by 1, so which gives B to be of the order m by 1. Okay, this is the system of equations that we would like to solve, and X is the unknown here, unknown vector. It's a column vector of coefficients x1 so on up to xn. Okay, and these are known, both A and B are known. Okay, now we are interested in understanding when solutions will exist. Okay, in that context, what we mentioned very briefly in the last lecture was that to recap very briefly what we did in the last lecture is that A can be represented as a collection of column vectors C1 to Cn, suggesting that the equation Ax equal to B can be written as B equal to x1 C1 plus x2 C2 plus so on up to xn Cn. Okay, so here B is a known vector, right, of order m by 1, and Cn's are known column vectors of order m by 1, and these are the unknowns, right, x1, x2 so on up to xn are the unknowns. So this appears like you're trying to expand a vector B in a set of vectors using a set of vectors C1 to Cn. Now the job will be easy if you have, suppose, m is equal to n and you had n linearly independent vectors in C, then you can always express B as x1 C1 plus xn Cn. That's a given, right? Because you can always express a vector in a vector B. Okay, if you have an n-dimensional space, right, you have n linearly independent vectors, you can always express any vector in terms of the basis vectors. That was not this is one of the simplest cases, but what we found in general was that if you need to have a solution, you have to construct what is called the augmented matrix, and you need to find the rank of this augmented matrix. Okay, what is the rank of any matrix? It's the number of linearly independent column vectors or row vectors. Okay, so you have to find the rank of the augmented matrix, and you have to find the rank of the coefficient matrix. Okay, if the rank of the coefficient matrix is equal to the rank of the augmented matrix, then there is a solution. If that is equal to n, the number of unknowns, then you have a unique solution. All this means is that you are able to expand the given vector B in terms of the column vectors of A. Now if R of A is equal to R of AB, but it's less than n, then you have many solutions. if R of A is not equal to R of AB, okay, then you have no solution. This is the case of an inconsistent system. Okay, we also saw that when you have many solutions, you can write it in the form of a single parameter family of solutions. Okay, so in the last lecture we saw an example of a single parameter family of solutions. Now in this lecture I am going to illustrate an example where you have a 3 parameter family of solutions. So example, so the equation that I am going to consider, okay, is the following: 2x2 plus x3 plus 4x4 plus 3x5 plus x6 is equal to 2, x1 minus x2 plus x3 plus 2x6 is equal to 0, x1 plus x2 plus 2x3 plus 4x4 plus x5 plus 2x6 is equal to 3, and finally x1 minus 3x2 minus 4x4 minus 2x5, okay, there is no x3, minus 2x5 plus x6 is equal to 0. So you have 4 equations and 6 unknowns. Okay, so you are trying to write B as x1 c1 plus x2 c2 plus x6 c6, right? But you know, you have 4 all these are this c1, c2 and b1, they are all 4-dimensional vectors. That is, they are column vectors of order 4 by 1, right? So there can at most be 4, because they are 4-dimensional vectors, there can at most be only 4 linearly independent vectors among C, but we have 6. So we can say that at least there will be 2 coefficients in this expansion which will not be found uniquely. That is, the solution that we may get will at least have 2 free parameters. So we can anticipate a 2 parameter family of solution. Okay, now we'll use Gauss elimination to reduce this to, I won't go into the details, you should be able to do it, x1 minus 3x2 minus 4x4 minus 2x5 plus x6 is equal to 0, x2 minus half x3 plus 2x4 plus x5 plus half x6 is equal to 0, and x5 plus x6 is equal to minus 3, x6 is equal to minus 5. Now these two are completely decoupled from this because they can be solved independently. So x6 is equal to 5, if I minus 5, sorry, if I put this minus 5 here, then x5 is equal to plus 2. Okay, now after this, if you substitute this out here, you still have 2 equations, these two, but there are 4 unknowns. So you cannot find all the unknowns uniquely. So you have to say, assume, let's say x4 is alpha 1, x3 is alpha 2. Then you will find from the 2 equations what is x2 and x1. x2 is half minus 2 alpha 1 minus half alpha 2, and x1 is 21 by 2 minus 2 alpha 1 minus 3 by 2 alpha 2. So you can find this. Okay, so I can write the solution as follows. I will write x vector is nothing but 21 by 2 half 0 0 2 minus 5. This is x5 and x6. Okay, plus alpha 1 minus 2, minus 2, 0, 1, 0, 0, plus alpha 2, minus 3 by 2, minus half, 1, 0, 0, 0. Okay, I am merely rewriting these solutions. We have already gotten x5 is equal to 2, x6 is equal to minus 5, and we have assumed these two because they are arbitrary, and then we found these for x1 and x2. I am writing simply all this in a condensed form, and I am trying to remove vectors that are independent of alpha and vectors that are functions of alpha. So there are two free parameters, alpha 1 or alpha 2. This is a two parameter family of solutions. Okay, so moving on further, we can do one more example. Suppose I have Ax is equal to B of the following form, where the augmented matrix is like this. You have 4 equations and 6 unknowns, let's say, right? So 1, 1, 2, 1, minus 1, 0, minus 1, 0, 1, 3, 2, 5, 3, 3, 1, 8, 0, minus 1, minus 1, minus 1, 2, 6, 7, 7, and the right side vector B vector is 4, 3, 9, 1. Again, you have fewer equations than unknowns. M is equal to 4, N is equal to 6. So you can again expect that you need not have unique solution. So we have to use again Gauss elimination. If you use Gauss elimination, upon using Gauss elimination, we obtain 1, 0, 0, 0, minus 1, 1, 0, 0, 1, 2, 2, 0, 3, 0, 5, 0, 0, minus 1, 0, 0, 2, 4, 1, 0, 4, minus 1, minus 2, 0. Okay. Now, the last row is completely 0 so this means that one of the equations in the original set was linearly dependent on the other, so that has come out as 0. So Gauss elimination removes that linearly dependent equation, so you are left with only 3 equations for 6 unknowns. So you have to by definition assume, and of course the rank of this matrix you can easily figure out by saying that, well, you can take this matrix, let me draw it slightly bigger. You can take this matrix and you can convince yourself very easily that this matrix has a rank of 3. So the rank of the coefficient matrix is 3. Obviously the rank of the augmented matrix is also 3, because even if you add one more vector, okay, it cannot increase the size of the determinant, right? So R of A is R of AB is equal to 3, but that's less than 6. So even though there is a solution, there will be multiple solutions. Okay, so effectively we have, therefore we have 3 equations for 6 unknowns. So we can think of x6 as alpha 1. You have to by definition assume 3 of the unknowns, x6, x5, x4. Let's assume it to be arbitrarily alpha 1, alpha 2, alpha 3.
So if you solve for the other two from these equations, you'll find that x2 is 1 minus 3 alpha 1 plus alpha 2 3, and x1 is 6 minus alpha 1 plus alpha 2 plus 9 by 2 alpha 3. If I were to write this in matrix form, then I will say x is 6 1 minus 1 0 0 0 plus alpha 1 minus 9 by 2 minus 3 minus half 0 0 1 plus alpha 2. I'm simply writing all this in matrix form. 1 1 0 0 1 0 plus alpha 3 9 by 5 minus 5 by 2, oh sorry, 9 by 2 5 minus 5 by 2 1 0 0. I'm simply writing these solutions in vector form. Now when you write, so this is obviously a 3-parameter family of solution. Why is it a 3-parameter family? Because you have the 3 parameters alpha 1, alpha 2 and alpha 3, which are arbitrary. Now there is an interesting aspect about the structure of writing the solution in this form. This turns out that x can be written as xp, which is called the particular solution, plus alpha 1 x1 homogeneous plus alpha 2 x2 homogeneous plus alpha 3 x3 homogeneous. Okay, this is called the particular solution, which is solution to A xp is equal to b, and these homogeneous solutions, these are called the homogeneous solutions, which are solutions to A x h I is 0. Okay, so these solutions, which are multiplied by alpha 1, alpha 2, alpha 3, are homogeneous solutions, whereas these are the particular solutions. Now how many what is the number of homogeneous solutions? Well, if the rank of the original matrix, so if R of A is, sorry, if R of A is R of AB is equal to n, then there are no homogeneous solutions. So you will only have a unique solution. But if this is less than n, depending on n minus r, you will have an n minus r parameter family of solution. So this, the number of solutions that you have is equal to, particular solutions that you have is equal to n minus r. Okay, in this case it is 3, n is 6, r is equal to 3, so n minus r is 3. That's why you have these 3 parameters. In general, it is n minus r parameter solution. Okay, now in general, therefore, if A is a m by n matrix, okay, and you are interested in solving Ax is equal to b, this system has a p parameter family of solutions as follows: x is x particular plus alpha 1 x h 1 plus alpha 2, where p is equal to n minus r, x h 2 plus alpha n minus r x h n minus r. Okay, so these are the homogeneous solutions. These are linearly independent homogeneous solutions. Okay, the space spanned by
these n homogeneous linearly independent solutions x1h to xh of n minus r is called the null space, and the dimension of the null space is n minus r. If r equal to n, there is no null space. The dimension of null space is 0. Okay, then the homogeneous problem has no solution, and you have only a unique solution. Okay, now right. So if you have m less than n, so ax is equal to b has either consistent or inconsistent solution. If it is consistent, you cannot have unique solution in this case, because you don't have enough equations as unknowns. So you will have a p parameter family of solutions. Okay, now if m is greater than n, then again ax is equal to b can be consistent or inconsistent, and here this p takes the value n minus m. Okay, it depends on the nature of the problem. If you have right, if n is equal to m, then there is no okay, sorry, if n is equal to m, this goes from 0 to n, otherwise it goes from n minus m to n. So this is the value that p can take, okay, in general, right? And if it is m greater than n, again you have unique, if there is a possibility of unique solution and a p parameter family of solution. And here 1 less than p less than n. Okay, now we'll come to some special cases. What if you have a homogeneous system? What are the conditions for a homogeneous system like ax is equal to 0? When will it have a solution? Okay, now here r of a is always equal to r of a b, because the right side vector b is 0. So this is always satisfied. That means that a homogeneous system is always consistent. Okay, that's because for a homogeneous system, the trivial solution of containing 0, this is called the trivial solution containing 0 vector, is always a solution. Okay, so that means that you're always bound to get the trivial solution. The key question is, when will you get non-trivial, non-zero solutions? Okay, when will you get non-trivial solutions? The answer to that is, if r of a is equal to n, then x is 0. You will get only the trivial solution. In order to get non-trivial solution, okay, if r of a is equal to r less than n, then you will have an n minus r parameter family of solution, non-trivial solutions. Okay, non-trivial solutions. Okay, so when r of a is r is less than n, this means that determinant of a is equal to 0 if a is n by n. If a is an n by n square matrix, then the rank of the matrix less than the order of the matrix implies that the columns are linearly dependent, so the determinant of the matrix should be 0. Finally, we'll have an n by n system inhomogeneous. Ax is equal to b. A is an n by n matrix and b is a n by 1 vector, column vector. Okay, here again, if r equals n, okay, that means that determinant a not equal to 0. That means that the matrix
A is non-singular and you have unique solution. When r less than n, you have determinant A is 0 and you will have multiple solutions. Okay. Now, so far we discussed everything in terms of rank. Now there is another elegant way of writing the conditions under which Ax equal to B will have solutions. Now the key thing that you should realize is that even for the same matrix, if B is different, then you may or may not have solution. So the key is to find what are the constraints on B for which you will have a solution. This is given by what is called the Fredholm's alternative theorem, or it is also sometimes called the solvability condition. Okay, so let's consider the adjoint of A, which is A dagger. You can easily verify that rank of A is the same as rank of A dagger. Okay, so A has n rows and m columns, whereas A dagger has the opposite, m rows and n columns. Okay, now you have to first solve for the adjoint homogeneous problem. This is the homogeneous problem for the adjoint matrix. Okay, homogeneous problem. Now if this has m minus r linearly independent solutions, let's call them Z1, Z m minus r. Okay, these are solutions of this equation, the homogeneous adjoint equation. Then Ax equal to B has a solution if and only if the right side vector of this B is orthogonal to each of the homogeneous solutions. Okay, so these are the homogeneous solutions. Okay, so this will put a constraint, or in matrix notation, the inner product of B and Zj has to be 0. This puts a constraint, this condition puts a constraint on B. If the homogeneous problem has only the trivial solution, this is always satisfied. That means your Ax equal to B has unique solution. Okay, that is always satisfied. Okay, so let's consider this or illustrate this with the help of an example. The solvability condition. Let's say you have Ax is equal to B, the Fredholm's alternative or solvability condition. You'll have two. Let's say A is this 2 1 1 2 3 4, operating on is equal to. Okay, so we want to know when, for what values of B will this have a solution. Okay, so first we have to do A dagger Z is 0. So A dagger is 2 1 3 1 2 4, operating on Z3. Okay, is 0. Now you can find the homogeneous solution to be minus 2 by 3 minus 5 by 3 1. Okay, that means that solvability requires, or the Fredholm's alternative requires, that B dagger Z is 0. That means minus 2 by 3 B1 star minus 5 by 3 B2 star plus B3 star must be 0. These are the conditions
on the elements of B in order for us to have solution to the inhomogeneous problem. Okay. Now there is one last topic with respect to solution of linear equation. I want to illustrate solution of Ax is equal to B via eigenvector expansion. That is, you have Ax is equal to B, and let's say that the eigenvalue problem for this same matrix A is A ei is equal to lambda I ei, and I am going to further assume distinct eigenvalues and orthonormal eigenvectors. Okay. So then I solve the eigenvalue problem of A, then I expand X as some alpha I ei, and I also expand B as some beta I ei. Okay, so I substitute the expansions here. So A summation alpha I ei is equal to summation beta k ek. Okay, I pull the A in because it's a linear operation. So summation alpha I aei is equal to summation k beta k ek. Okay. Now I want to find alpha j, so I have to take the inner product, because you know that ej ei is delta ij. It's an orthonormal set. So take inner product with respect to ej on both sides. Right, so you will get I alpha I. Now first, before I do that, you have to realize that aei is nothing but lambda I ei from the eigenvalue problem that we just wrote here. Okay, so I have alpha I lambda I ej ei is summation k beta k ej ek. Now we know that if it's an orthonormal set, this is delta ij, this is delta kj. The deltas will kill one of the sums on both sides to give alpha j lambda j is equal to beta j, or beta j, the coefficients of is equal to, or sorry, alpha j beta j by lambda j. Once you find alpha, you can find the original unknown, because once you know the eigenvectors, once you know all the alphas, you can use this expression to reconstruct the solution in terms of the eigenvectors. Okay, so this constitutes a solution. So alpha j is beta j lambda j. This forms the solution to the system Ax equal to B. All you have to do next is to simply use this expansion to reconstruct the solution. X is, so we have found alpha j's, so x is nothing but summation alpha j times ej. Okay, this is the solution. So there are multiple ways of solving systems of linear equations. The key thing to understand is the notion of solvability, right? That's very important. It's not that all linear equations are solvable. We have to understand the rank criterion in order to see how many linearly independent solutions are there to the homogeneous problem. Accordingly, you will find so many parameter value of solutions. Okay, so I'll stop here for this module, and we'll start function spaces in the next module. Thank you.